Similarly, if you substitute a cation which changes the crystal symmetry of say 10% of the total, because you are not replacing all the cations, you are replacing only 10% of that specific site, and the structure is different, then your material is 10% that structure and 90% other structure. So you introduce, for example, 10% tetragonality into the cubic structure, 10% tetragonality into cubic structure. So in this way, you can play with all aspects of material. There again, we got excellent properties. The dielectric constant increase at x equal to 0, this is almost that. But when I increase the amount of titanium, because the titanium dielectric constant is high, and it forms a titanium-based new phase, and that new phase. But when I found that new phase, why not make that new phase as a single phase material and look into its property? If the material is enhancing the property, then let us look into the new phase. And in this way, the train of research goes forward. So when you end a movie, you are watching a movie and it ends up, it starts about a person. But when the movie ends, he has many kids. And now you can make 10 more movies on that. Right? The same thing is here. That when you search in the ocean of knowledge, you had gone after one thing, but there you see many more things. And that moves the train forward. How the material cracks. I have just selected this small picture for its thermal expansion coefficient. Look at it. The thermal expansion coefficient of anorthite, which is calcium aluminum silicate, it is 4.3 into 10 power minus 6 K. Glass of the same composition or similar composition. Remember that, not ordinary glass. Glass of the similar composition, its thermal expansion coefficient is 3 to 4.5, 10 power minus 6. Why 3 to 4.5 into 10 power minus 6? Because the composition is not homogeneous. When you are having a complex material, the composition is not homogeneous. How can I guess that what should be the value of composition? I am making something. As you saw, strontium niobate and strontium titanate. So I take an average composition between the two. Or instead of average, say 10% one and 90% other. So if I vitrify means when I transform materials and those ratios into glass, what will be its thermal expansion coefficient? Then I will compare with that. So nothing is by chance. Everything logically, quantitatively, qualitatively, scientifically verified and tested, not blindly. If I have made this material and this much has been transformed into this crystal phase, how much will be glass left and what will be its approximate composition? And when I studied it And as you remember, I showed you that I measured the composition of glass in different regions. Then I averaged them overall. And then I looked into the dielectric thermal expansion coefficient of that glass. And then the thermal expansion coefficient of beta TCP, beta tricalcium phosphate. When the thermal expansion coefficient is different, what happens? One part of the material compresses, shrinks, the other part expands. What will be the result? Breaking the material into pieces. Stress and strain, they are in competition and they are locking things. But when the lock is disrupted, they will break. The same you see and when rainwater gathers somewhere in fine particle land, after some time cracks appear there. This is because of the thermal expansion mismatch in the region, right? So, how properties are predicted, detected, controlled, and engineered in material science is a very, very simple but very, very tough and systematic job. It is not difficult and never difficult. All the world is doing it, and it doesn't need somebody from heaven. People like you and me are doing it. So come, move forward, struggle hard, systematically. The life will finish whether you want it or not. You will work up to the end of your years whether you want or not. But if you do it excellently, you will feel proud, the department will feel proud, the nation will feel proud, and the world will feel proud of the mankind of this time, period. And if you waste your time, you are a burden on yourself, your parents, your village, your city, your country, and the whole humanity. So don't become a burden and become excellent scientists and contributors to the field. And now it's open for questions, please. In the next lecture, we will start X-ray. Nucleation gives free energy. Nucleation, I told you that when the crystallization starts from the melt, you have a glass melt and you start to crystallize it. The first step will be the gathering together of the energy-wise more feasible structural units, and that will form crystal nuclei. The crystal nucleation theory, when you study in detail, they say that there is a critical size, right? If 5 hands make a structural unit and that nucleation reaches that 5 level, the nuclei will grow. If they don't reach there and stop there, then slightly short range order was introduced, but it couldn't continue for long range and nucleation will stop, right? So if energy wise it is possible, if no energy is required and the reaction, usually it is exothermic, then they will come by themselves together. The more the potential to crystallize into specific phase, the quicker crystallization will occur there. The quicker the crystallization, the faster will be the growth. Also, I told you that fluidity of the matrix is also must, because if there is potential of crystallization, but kinetics doesn't allow, don't allow it. Kinetically, it's not possible. Mass transfer is not easy. Then obviously, this will hinder the crystallization process. So, crystal nucleation is basically the initiation of crystallization, and crystal growth is the building up on the same nuclei. This is the thing. And their dependence is both on energy and both on the fluidity of the melt, and there may be also some intrinsic, what you say, uh, properties or features associated with the planes, because some planes coming to put the new material, mass transfer to the some planes is much easier and favorable in comparison to the other. So you will see more growth there in comparison to the other. And maybe that is also a reason that some crystals grow in one direction and some in other. Yes, please. Mishra. So what did you learn from these all things? I tried to brainstorm you, right? I took you here and there. I brought XRD, I brought TM, I brought ECM, I brought DTA, DC, TGA, material tailoring, composition, just to give you a walk, a move in a field of material, that what people do and how people do. And in my opinion, I succeeded in ending up your fear of research. That research is not something unusual. It is a usual routine thing. One person is selling things, the other is making things, the other is designing things, the other is proposing things. Right? So the researcher is basically a proposer. He proposes something, then works upon it, and when that succeeds, it goes to production, and that production then affects the economy of the country, of a nation. And similarly, inventions and innovations result in the world. How much innovation and invention is needed? People have started again bringing rocks into the markets. They want their homes to be natural. They don't want their homes to be artificial, as people tried during the last century. But this century has felt that everything unnatural is not good. We must be natural. So whatever you do, think about it. Is it worth it or not? If I am doing something which is giving discomfort, but how much loss is it incurring upon the humanity, upon the living things, upon the nature, upon the environment? And I am again and again telling you that do positive things. Don't move towards negative things, because when negative thing is there in the world, it will be used and again on the living things, and that may be you. So don't create killers for yourself. Always favor better life and natural life. Favor nature, protect environment through your material science, through your physics, through your daily life, and help the humanity live a happy life and let others live a happy life. Thank you very much.